Hello everyone, welcome to the LLM show, and I'm your host Shamin Siri. In today's episode, I actually want to talk about transformer reinforcement learning library from HuggingFace, which is pretty awesome. With this, we just can apply reinforcement learning from human feedback with a few lines of codes. We all know reinforcement learning from human feedback plays a major role in custom applications that uses large language models like ChatGPT and even Llama version 2 chat. So this library mainly uses this specific reinforcement learning technique called Proximal Policy Optimization. In order to understand the code, like what is happening inside this library, it would be kind of important to understand some core concepts related to the deep reinforcement learning. So in this video, I kind of want to summarize them, and this is not a video that I would explain all the concepts in details, but I would try to explain these jargons, because explaining reinforcement learning in a one video is not a practical thing. You actually need to spend some time on this exact machine learning paradigm, right? So yeah, let's start with what is reinforcement learning. So reinforcement learning is all about optimizing an agent to take optimal set of actions in order to maximize the expected sum of future rewards. So with deep reinforcement learning, agents can directly learn from raw sensory inputs and make sequential decisions in complex environments. Unlike supervised learning, where agents learn from labeled examples with explicit target outputs, in deep reinforcement learning, agents can learn from cumulative rewards rather than explicit guidance, right? So that's pretty much the difference in deep reinforcement learning from supervised learning. And yeah, we are talking about deep reinforcement learning because of this instruction fine-tuning. You know these steps. First you take your large language model checkpoint, then you fine-tune it with your instruction fine-tuning dataset, then you train your reward model. Given an output from ChatGPT, it can then output some sort of a scale reward. Once you have a reward model, what you do is you kind of plug it with the reinforcement learning from human feedback setup, and then you fine-tune your large language model to get better outcomes, right? So this is pretty much the reinforcement learning from human feedback setup. So why RLHF is important? Because it kind of can improve the outputs from the agent, and also it can also reduce things like toxicity, right? Because this can directly give some sort of a feedback about the generated output to the model, and model can kind of learn, and yeah, we can keep doing it. So when it comes to the transformer reinforcement learning library, they use this specific reinforcement learning technique called Proximal Policy Optimization. There are different types of reinforcement learning algorithms, but yeah, PPO is some sort of a PPO is a very engineering friendly algorithm. It's been introduced by it was introduced by OpenAI peeps around 2017, and actually I worked a lot with PPO back in my masters around 2018. It is a very stable library, and also it is sample efficient, and yeah, it also kind of can balance between exploration and exploitation. This is an important thing when it comes to reinforcement learning. So if we write a pseudocode, what happens with the proximal policy optimization is like you have an agent or an actor can take bunch of actions. Then every time when you take an action, you will change your current state, and then you get your rewards, and then you compute something called advantage, like how good your action is, in terms of your end goal, and then you collect everything, then you optimize this agent in order to take better actions, right? So this is like the proximal policy optimization setting. And yeah, Please read if you want to know further about PPO. This is an amazing algorithm. So in order to kind of understand what are the main terms in PPO, you actually need to understand policy gradient theory. So policy gradient algorithms optimize the parameters of a policy by estimating the gradient of expected rewards and updating the policy in the direction of higher rewards. That means in policy gradient methods, we directly optimize our model to get the best action. So if we write the loss function in policy gradient, this is it. So it has two parts. This is like the action probabilities, like given in a state, what is the probability of outputting this action. And then we have another part called advantage, like how good that action in this state in terms of the final goal, right? So this is like an expectation operation, and yeah, we just need to optimize this. So this is same as supervised learning, softmax cross entropy loss, but in reinforcement learning, especially in policy gradient, this is the loss we use. Right now we try to understand each part. First we go through this part, like action probabilities. In practically, we don't use this part only, because the thing is then we can introduce a lot of instabilities to our algorithm, like for example, like if we keep updating only with this current action probabilities, our model could go to a black hole. So what we do is we use something called we call this the ratio function. So the idea is it's a ratio between the current policy and the previous policy. By doing this, we kind of reduce the variance in the optimization, and also we can handle non-stationary factors. Like in reinforcement learning, the policy is often updated during the learning process. So we call this stuff as like on policy gradient, on policy algorithms. This introduces a challenge known as non-stationary, where action probabilities used for collecting data differ from those used during the policy update. So every time when you need to change your policy, even by slightly, right, because you update your parameters, then the data your algorithm sees can change. That's the whole point of this. So having this kind of a ratio can reduce that, right? So basically we don't use this current policies action probabilities in the optimization, but we take a ratio. Then what is this advantage function, right? So the advantage estimate in PPO provides a measure of how advantageous an action is in a given state, allowing for more accurate evaluation of action quality. So that's pretty much it. Like and then having an advantage function helps you to kind of optimize your algorithm and kind of guide that algorithm to kind of get higher rewards in future. That's the whole idea. PPO uses as a guiding signal to update policy, enabling more effective optimization by favoring actions that lead to higher advantages. So I'll explain a bit. So imagine you take an action with your current policy, which is like drastically different from your previous policy. Like so that means that there's a huge difference, right, between this ratio, and your advantage is actually a positive one, which is a good one. So you can say like, oh, I should change my previous policy because this is a good advantage. This is a good feedback for me. If this is negative or this is not good, so then what you can do is you can kind of say, oh, I should not update my policy like this because I'm not getting any good feedback. I should kind of go back to my previous policy, so something like that. So that's how advantage can kind of guide the entire optimization. So again, then the important part is how to compute this advantage. So like in practically, this advantage function is also an estimation, because it kind of says like how good your action in a state by averaging all the possibilities. So practically you can't average all these possibilities, so you actually need to estimate it. So usually we estimate it with something called TD error. This is really an important concept in reinforcement learning, temporal difference error. Please read it like if you want to know further. I really like this concept. This is like a core concept in deep reinforcement learning or any reinforcement learning algorithm. So the advantage estimate subtract the estimated value function from the observed return. So this is what you have estimated, and then this is like the immediate reward, and this is like the value function of your next state, or your like when you move, like when you take an action, this is like the next state. And we call this as a discount factor, because you need to discount the future. So it's discount factor is basically like, you can say like you can't guarantee that you will get the same value for your money that you have today in 10 days of time, right? So you need to kind of discount it. So this is how you compute the advantage function. Now you might be thinking, what is this value function? So value function is again like a function approximation. So it kind of gives an idea about total rewards that we can get from a certain state. In a PPO setup, what we do is we actually predict this with another network. That network takes this observation or like the state, and then it can kind of output a scalar. So let's see how this PPO algorithm would look like in an architectural diagram. So this is it. We call these kind of models as actor-critic models. You can see you have a bunch of layers shared, and then one head directly predicts the action, and the other head directly predicts the value function. So basically you train this stuff jointly. Okay, so this is how PPO algorithm would look like in an architectural diagram. And there are few other things to kind of cover when it comes to loss function. Although this previous loss function, again, we can't optimize it, because the thing is, imagine your current action probabilities are high and your previous action probabilities are low, and there's a huge value here, right? Because this is low and this is high, and yeah, so ratio is high, right? It's a big number. And then you have some sort of an advantage here as well. Imagine if we keep updating our model with this ratio and this advantage function, this model can again like introduce a lot of instabilities to the optimization, because if the updates are like, if these updates change our policies with a huge margin, it can really create a lot of instabilities in the training, right? So because of that, PPO introduced something called a clip loss function. You just don't update your model only with these values, but what you do is actually you update your loss function in certain regions. So theoretically we call this kind of stuff as trust region methods. So art behind clipping, this is a figurative explanation into the PPO's loss function clipping. There are 3 situations, and they kind of explain this clipping phenomena perfectly. So yeah, the x-axis is the ratio between action probability of the current policy and the action probability of the previous policy given the same state, and the y-axis is the loss function, right? And a is the advantage. So in the first case, the advantage is good. That means your algorithm has taken a decision, and it has got a really good feedback. But if the ratio is too large, that means your current action probabilities are kind of larger compared to the previous one. If it is too different, you don't get too greedy and update your model. You are like, no, I'm not going to update after this. I'm only updating my parameters in this region. So you are not not going to be too greedy, right? And then in this case, what happens is like advantage is negative, like that means you have taken a decision, but it is not giving any good feedback. So again, you are not going to make you are just not going to make the action probability of the current policy into 0. Just like, just wait, don't keep reducing after some level. So that's the clip region. And yeah, this is the second scenario. And the third scenario is like when your ratio is large, that means like your current action is really different from your previous policy, and yeah, it is very, I would say, it has a high probability as well. And then and also advantage is like negative. And if it is too different, what you do is like then you just take that update out. What you're saying is like, here, okay, this is not a good update, just convert my parameters back to my previous policy. That's pretty much it, what happens. So yeah, this is what happens in the clipping. Yeah, so end of the day, this is the clipped PPO loss function. It's a minimum operation. This is the normal loss ratio function and the advantage, and this is like the clip part, right? And it is also important to note that I said like value function, right? We have in value function also an estimate, and we use a different neural network head to kind of output this value function. We also need to optimize that. So we can optimize that with the mean squared error, because this is like the discrepancy between the predicted and the observed value. This is the this is like the value function in your in the current state, and this is like more like the observed values. So what you do here is actually you again kind of estimate this observed values with TD error. That means the value function of the next state plus the immediate reward. So that's pretty much it about the value function optimization, right? So when it comes to the total loss function, when you go to the code, see something like this. So this is the loss function of the clip, and this is the loss function of the value, and also we have something called entropy bonus. This is also a loss function. So the idea is you don't want your policy to like take two extreme actions, like let's say one action probability is closer to the 1 and all other action probabilities are like closer to 0. That's not good, because then your model won't keep exploring. So this will kind of encourage the model to explore more, like kind of give like kind of similar probabilities to all the possible actions in the beginning, and like so you can encourage the model to explore and exploit. So that's pretty much the loss function. The proximal policy optimization theoretically, and this is like the proximal policy optimization set up in reinforcement learning from human feedback, especially with language models. Now the thing is, you need to map some of those concepts from like theoretical proximal policy optimization to PPO in RLHF. So the first thing is, in RLHF every action is like generating a new word, right? But we don't get a reward for every word, because that's not how we have trained this model. So we just need to first output a like we just need to get the full output from the LLM, and then we need to send it through this model. That's where we get the reward for every for the entire generated sentence, right? So then training on that can actually create a lot of instability. So for that, what we do is we add this KL penalty. That means we need to make sure the action probabilities between your current model versus the base model. Base model is the large language model that's been trained with the instruction fine-tuning data, so you add this KL term. So basically your reward term is like this. Actually, this is like the total reward, and this is like the KL divergence term per word, so by this we kind of can transform the reward. This is how we actually compute the reward function per word. We will get understand this when we go through the code, but this is pretty much the idea of proximal policy optimization in RLHF. Yeah,